We have seen that the derivative of a function is actually a new function. And now to get these new functions, there are a whole bunch of rules for differentiation. In this video I will cover a few of the rules, but not all of them. So I start with a few notational comments, and then I look at the two rules, one for constant multiples and the other for sums and differences. And these two rules are really super simple, and we can just blast through them. Then the power rule, the product rule, and the quotient rule is really the topic of this video. And then the chain rule, the implicit differentiation, and the logarithmic differentiation, I leave them for later videos. Since the derivative is so important, there are actually several notations which are used in parallel. So we mean f prime of x with a derivative. Sometimes we just use f prime or y prime if y is equal to f of x. Or we write it as a ratio df by dx, but this is not actually a ratio, it is just a notation for the derivative, or dy by dx. Now if we evaluate a derivative at a point x is equal to a, we use a vertical line. So f prime of a can be written as f prime and then the function evaluated at x is equal to a, or df by dx evaluated at x is equal to a. We can even build higher order derivatives, so which means derivatives from derivatives. So for example, f double prime, this would be the d by dx of df by dx, or we write this as d2f by dx squared. It looks a little bit strange, but this is a notation you will get used to very, very quickly. F triple prime, for example, would be the third derivative, and f in brackets n is a notation for the nth order derivative. Let's come to the first two rules, which I promised you were the simplest ones. So the constant multiple rule is as follows. So you have a function f, you multiply the function by a constant c, and then cf prime is c times f prime. So a constant factor can always be taken out of the derivative. Rules for sums and differences are exactly as you expect. For example, if you have f plus g prime, this is in fact f prime of x plus g prime of x. And then for minus, f minus g prime is f prime of x minus g prime of x. The power rule is actually really cool as well. It says if you have a function f of x is x to the r, and if you differentiate x to the r, you get r times x to the r minus 1. Yes, indeed, we have seen one example previously where we had the function f of x is equal to x squared, and then we found f prime of x is 2x. Here now r is equal to 2, so d by dx of x squared is 2 times x to the 2 minus 1, which is 1, so it's 2x. So this satisfies the power rule indeed. But let me give you another example. F of x is square root of x. Okay? So square root of x is of course x to the 1/2. Alright? And so then we could use the power rule with r is 1/2. Let's do that. So then this means f prime equals r x to the r minus 1, and r is 1/2. So then this comes out to be 1/2, and then x is x to the power of 1/2 minus 1, which is minus 1/2, okay? And so then I can write this as 1 divided by 2 root x. So if f is root x, then the derivative is 1 over 2 root x. In this case, I like to go back to the differential quotient and compute this explicitly and see if we are correct. So f prime at x equals limit as h goes to 0, f of x plus h minus f of x divided by h, which is then subbing in the function limit as h goes to 0, square root of x plus h minus square root of x divided by h. And now comes a trick which I like to show you, which is called rationalization. You multiply with the conjugate term. So what you do is you multiply with this term here, root of x plus h plus root of x divided by root of x plus h plus root of x. And this is the reason why I show you this example in so much detail, because this trick is a wonderful exam question, and I bet you this will come back in some quiz or exam. So it is worthwhile to be able to do that. So I do this. First of all, the green expression in itself is 1, right? It is just 1 written in a fancy way, so really nothing happened. But if I multiply the green expression to the numerator on the left, then I have basically a minus b times a plus b, which is a squared minus b squared, and it gets rid of the roots. So this is cool. So then we have limit as h goes to 0. So we multiply this out in the numerator. Then we get the square, which is x plus h, minus x. And then in the bottom we have h times square root of x plus h plus square root of x and bracket closing. But then the x terms cancel in the numerator. Limit h goes to 0, and we get h divided by h root of x plus h plus root of x. And then the h's cancel, and we keep a 1 here. Then this is limit 1 divided by root of x plus h plus root of x. But now I can safely take the limit. As h goes to 0, then this term here just becomes root of x. In fact, we get 2 root of x in the denominator. So this is 1 divided by 2 root x. And now you see, haha, we do get the same as we computed by the power rule. So this means the power rule is correct, at least for root of x. But of course the power rule is correct for all kind of values of r. I have 2 more examples for the power rule on the next slide. Let's look at f of x is a constant value of 17. And I want to do this with the power rule. But I don't see, how is this x to the r? Well, I just write it very complicated now. I write this 17 times 1, which is then 17 times x to the power of 0. And then in combination with the constant factor rule, I can write f prime at x is 17 times d by dx of x to the 0. Let's just do this for fun. So then we have 17 times 0 times x to the minus 1, which is 0. So the derivative of a function constant equal to 17 is 0. And this in fact is true for all constants. So what we learn from this is if f of x is constant, any constant, then f prime of x is actually equal to 0. And then one more example. So let's do a polynomial. Let's say f of x is 5x cubed plus 4x squared plus 6. And then the derivative is f prime of x. So 5 is a factor which I can leave. X to the 3 I use the power rule. This is 3 times x squared. Plus 4, I leave the 4. X to the 2 I use a power rule, which is 2 times x. And then plus 6, but 6 is a constant. The derivative is equal to 0.
Which equals 15x squared plus 8x. And we are done. So you see, using these rules, we can differentiate more and more complicated functions over time.
Let's come to the product rule. So the product rule has 2 functions f and g, and I look at the product f times g and then the derivative prime, and this turns out to be f prime times g plus f times g prime. So it is not, you might think this could be f prime g prime, but this is absolutely wrong. This is something you cannot do. It is f prime g plus f g prime. So also here I have an example. So let's look at a function that maybe h of x is x plus 2 times x plus 3. Okay, so then this is also f of x times g of x, with the obvious choices of f is x plus 2 and g is x plus 3. Now look at the product rule again. You do need the derivatives of f and g on their own. And we can do this now. So f prime of x is 1, okay, and g prime of x is 1. Derivative of x is equal to 1. Derivative of 2, which is a constant, is 0, so this goes away, and the 3 goes away. Fg prime of x is f prime of x times g plus f of x times g prime of x. So then f prime is equal to 1, g is the function x plus 3, f is the function x plus 2, and the derivative of g is 1, so we get this. And then multiplying this out, we get 2x plus 5. So, and that is a new derivative of the product function. The last rule for this video is the quotient rule. Now the quotient rule is in fact a little bit more complicated than the other ones. We have two functions, and we look at the ratio f divided by g, and then the derivative. And again, we can compute this by the derivatives of g and f, but in this kind of complicated form, gf prime minus fg prime, and then divided by g squared. But luckily, some smart people came up with a little song or a little rhyme, which helps us to memorize this thing. So it says, low d high minus high d low, draw a line and square below. Right, so this low refers to g, d high means the derivative of the numerator, which is f prime, minus high d low, so high is the f, d low is derivative of g, and then draw a line and square below. That's it. This saying is quite useful to memorize the quotient rule. Let me give you one example which is kind of interesting. Let's look at the function h of x is x squared minus 25 divided by x plus 5 for x positive. To use quotient rule. So what is which? So the high function is the f function, which is x squared minus 25, and the low function is the g function, which is x plus 5. We do need the derivatives, but we can use the power rule already. So f prime of x, right? So the derivative of x squared is 2x from the power rule. The constant 25, the derivative is 0, disappears. G prime of x is 1, derivative of x is equal to 1, and the derivative of 5 is 0. So these are the two derivatives. Now we can use the formula. So f divided by g prime of x is, how does it go? Low d high minus high d low, draw a line and square below. Good. Sub it all in what we have. So g is x plus 5. Okay, derivative of high is 2x minus f is x squared minus 25, and g prime is equal to 1. And then we square x plus 5 squared. So, looks complicated, but now it will simplify. So we multiply this out, we get 2x squared plus 10x minus x squared plus 25 divided by x plus 5 squared. And then the x squared terms in the numerator simplify, we get x squared plus 10x plus 25 divided by x plus 5 square. But now it is complete square in the numerator. We can write this as x plus 5 square divided by x plus 5 square. Ha! And this is equal to 1. The constant multiple rule says Cf prime is Cf prime. Rules for sum and differences say f plus g prime is f prime plus g prime, f minus g prime is f prime minus g prime. The power rule says that the derivative of x to the r is r times x to the r minus 1. What else? Product rule. So f times g prime, this is f prime g plus f g prime. And finally, the quotient rule, this would be f divided by g prime. So this is low d high minus high d low. Draw a line and square below. Here we go. So these are the first 5 rules for derivatives, and they are very, very useful. You just simply need to know those.
Tolo, what is this? Oh, you are working on your power rule? And does it work? Sure, it does work. Awesome, you look good.